Hello, everyone. Welcome to part 2 of geometry. So, our focus will no longer be on proving things, but our focus will be on using geometry to find missing parts or answer questions. So, part 1, right triangles. So, this we're talking about special and unique aspects of specific right triangles. So, the first thing we need to do is we need to define this idea of mean proportional. So, if you recall in our last unit when we did similarity and we had our proportion A over B equals C over D, we said B and C were the means. Well, now we're going to talk about a mean proportional. So, a specific type of proportion called a mean proportional where the mean values are the same amount. So they're the same side and the extreme values are different. So to find the mean proportional between 4 and 16, what this means is 4 and 16 are extremes. So that would be 4 over x equals x over 16. So this is a mean proportional because our mean values are the same. So when we cross multiply, we get x squared equals 64. Then to solve, we can take square root of both sides. So we say x equals plus or minus 8. When we consider only the positive value of this mean proportion, it's called the geometric mean. So the geometric mean of this problem would have been 8. So for example 1, find the geometric mean of 15 and 20. We're going to do 15 over x equals x over 20. We cross multiply, so we get x squared equals 300. And then it says leave our answer in simplest radical form. This time when we're taking the square root, because we're finding the geometric mean, we do not have to do the positive and negative. We're only doing the positive. So x equals square root of 100, square root of 3, or in other words, 10 radical 3. So why is this important? Well, sometimes you'll be asked just to find the geometric mean, which is different than the typical mean, which is your average. And it also happens to be an important case in right triangles. So, special cases with similar triangles is if I have a right triangle. So, here's right triangle ABC, where C is my right angle, and I draw the altitude from the right angle to the hypotenuse. I create 3 right triangles. And not only do I create 3 right triangles, but I created 3 similar right triangles. So triangle ACB, which is our large right triangle, is similar to triangle ADC. And that's because they angle. They share angle A, and they both have a right angle. Both of those are also similar then to triangle CDB. And that's because, again, they both have a right angle if I'm comparing the large, and they both share B. So those 3 triangles are similar. And that gives us some special proportions. So those special proportions that we can say is that I could say that AC is to AB So I can do it that way, but that actually is not how I want to do it. I want to do it the opposite. So I want to say AB is to AC as AC is to AD. So for that, I'm using our first 2 triangles. So I said AB corresponds to AC as AC is to AD. So that is the mean proportional. AC is the mean proportional because it's the same, which we'll often refer to as hills, which is our whole hypotenuse is to the adjacent leg as that leg is to the adjacent segment. Now, another proportion we can do is I can say that AD is to DC as DC is to DB. And for that proportion, I'm using these two similar triangles. And notice again that I have a mean proportion. DC is the same. And that we refer to as SAS. So that is the segment part of the hypotenuse is to the altitude as the altitude is to the other segment. So hills and SAS are important things to remember for these special right triangles. So how can we use this? So I can use hills and SAS to solve these three problems. So when I look at letter A tells me I want to use hills. And why I know I want to use hills is I don't know the altitude. So if I'm using hills, I'm going to say the hypotenuse is to the leg as the leg is to the segment. And I always want to use the segment that's closest. So the whole hypotenuse is 12. So I'm going to say 12 is to Y, which is my leg, as Y is to the segment that's closest to that leg. So it's 3. So that gives me Y squared equals 36. So then Y just equals 6. And I only have to use the positive value because I'm doing the mean proportional. So then for the second example, I'm looking for the altitude. So since I'm looking for the altitude, I'm going to use SAS, which is segment 1 is to the altitude as the altitude is to segment 2. And another way to think of this is you can think of this as it makes an altitude symbol. So segment 1 is 4 is to my altitude X as X is to the segment 2, 12. I cross multiply and I get X squared equals 48. Take square root, so X equals the square root of 48, which in simplest radical form is the square root of 16, square root of 3, or 4 radical 3. I want you to pause and try the last example on your own. So in this last example, I want to use SAS because I'm looking for the altitude. So I'm going to say 2 is to 3 as 3 is to X. So 2X equals 9. So X equals 4.5. So that is the end of our notes for today. If you have any questions, please ask me tomorrow in class while we're working on the classwork.